Are you going to tell me something? Those who read went to the website. Notice there was a professor Polly who was going to come. Professor Polly is editing a big volume of, there's going to be of articles, what happened, and mine has 45 pages, so imagine it's going to take something like that in the library. But with so much work, he was stressed and decided not to come. Then I called my friend, not quite friend, but somebody I knew, very much person, a professor from Greece who was in Strasbourg, and he told me, oh yeah, Professor A'Campo, I have to be here in Dublin, and I said, for me it was an unknown, but we met very soon, a few days ago, and I was very impressed because of his perspective of topology. I said, oh my God, topology is not as boring as I thought it was. So it is my great pleasure to introduce. He's going to talk about his perspective because he has a very liberal and interesting perspective about topology and the development of settings. I'm disappointed about it. Do you want to okay. You have to leave something tomorrow. Okay. What do you think? Oh, the idea is effective. Stop there. But he has some
I'm very glad to be invited here to give lectures on a topic which I like. The title was, I had quickly to make the title. Title should sound good, so I said Riemann surfaces as I think meeting point between algebra, topology and geometry. The order of the three things I forgot. And for me, they are not ordered. And so I'm glad to do this. So Riemann surface is a topic which is just complicated enough that you can do something. And at the same time, it is as easy enough that you can make many things very concrete. So it is good topic to, I think, good topic to learn if you wish to do mathematics. And the topic is very old. The name Riemann surfaces came after Riemann, which is roughly 150 years old. But of course, Riemann surfaces existed much before Riemann. But not, he was able to give the definitions, the working definitions, even the definitions which we use nowadays. So, therefore, it's good to say Riemann surface. So, I do not give in my first lecture what is a Riemann surface, that's too fast. But I say our object of study is a couple of two things. This is a surface, and this is something else. And today we work on the side surface. And the surface can be extremely complicated. So what we do is we try to think about surfaces which are not extremely complicated. So a surface is something which locally looks like the Cartesian plane. So if you have the Cartesian plane, and when you say locally, it means you take a point and in the vicinity that is locally, you have here something else. And every point here has a neighborhood which matches with the neighborhood in the plane, then you say you have a surface. So typically, what is not a surface, so the letter y is not a surface. If I take such a point, the neighborhood looks like an interval. And there's no point such that the vicinity of that point looks like an interval. And this is also different. But if I attach something here, like this, then partially this space is a surface. When I take a point here, then I can find a neighborhood which matches the neighborhood of the plane. If I take a point on the border here, then already here I have not strictly speaking a surface. We have something which we call surface with boundary. So what is surface with boundary? Surface with boundary is you take from the plane only half of the plane. So the plane, you take only this part of the plane. And now if I take a point on the boundary, I must look for a point somewhere here, such that the vicinity, I must look for a vicinity, for a neighborhood here, which I can find back here. So a neighborhood here looks like this. So when I try in the middle, it's not possible. So I have to try somewhere here. And when I take something here, then you see you can make a bijection, continuous bijection, continuous in both directions from here to here. So that would be surface with boundary. So when we say surface, that means there's no point which has a vicinity which looks like a point on the border in the half plane. So surface. So we work only with surface, not with surface with boundary. And then we also wish that the surface is from a topological viewpoint not too complicated. So we ask that the surface is connected. Connected means if you have 2 points on the surface, you can find a continuous path from one point to the other. So a non-connected surface would be if I take this and this, a point here and a point here, and I wish to have a path has to leave the surface, so connected. Then the other thing what we wish is compact. Compact means each time we have a sequence in our surface, we can find a subsequence that converges to a point of our surface. That's compact. So a non-compact surface would be if I remove from the disk in the plane, if I remove the boundary. Then I have a non-compact surface. I have a surface because there's no boundary. I remove the boundary. I can say surface, not surface with boundary. So I have surface. But when I take a sequence of points that converges to a missing point on the boundary, then this sequence has no subsequence that converges to a point of the surface. I introduce another. Okay. So that's the word compact. Then, next simplification which
would you mind reading about compact? Because we are having problems for what we can see without two master.
the word compact.
Yeah, okay. Oh, the last few sentences, because we were stuck here. Because of the two master.
You wish to have. So
that's it, right?
Let's take the interval. That's all of the numbers between 0 and 1. And then I can take the interval, but only the numbers which are rational numbers. So this one is compact, this one is non-compact. So for instance here, I have a number, square root of 2 divided by 2. And this I can approximate by rational numbers as much as I want. So I only remember the first decimal. But this continues. And if you put here at step n, you get a sequence of rational numbers which converge to this number, but does not converge to a number belonging in this set. This number does not belong to this set. But it is a not so easy statement that the interval 0, 1 is compact. So I say not so easy. Euler did not know this. So Euler is kind of young in mathematics. Archimedes is older than Euler, a very young person, and he did not know this. And in a century ago, no, I must say 2 centuries ago, so between 1800 and 1900, this work was a work with a lot of controversy. There was a lot of fighting about this. So I think it is Weierstrass who stressed that we need this work in mathematics. So the famous problem in those days was, if you have a curve in the plane, you can ask for which curve of given length bounds the region of maximal area. And there were proofs for the fact that this region must be like the Euclidean disk. But the proofs, they assumed the minimum exists. The Weierstrass said, yeah, if you assume the minimum exists, then clear, you have a proof. But if you don't assume this, your proof is not a proof, because they use the sequence and they use the convergent argument. And so how do you know that the sequence converges to a point of your set? Of course, people say, yeah, I only see the things I can draw. But that's very dangerous. Perhaps there exist things which you can also draw, but you personally don't see them. So Weierstrass was the man who said the word compact is important. And then there's another word which is oriented. Oriented is something which everybody knows. I draw for you a non-oriented surface. This is the Möbiusband. And this is non-oriented. If you stay up here and you walk along this path, you come back, then you look at the other side. And this is the bad definition of orientation, but it's a good example. Because what I use here, I use that the surface sits in 3 space. We should have a definition of orientable and non-orientable, not depending on the fact that we sit in 3 space. So this definition is very clear, but also not a good one. So if somebody knows the good definition, we draw a Möbius strip again, and now I forbid itself to use vectors which point out of the surface. And I wish to say this surface is not oriented. What do I do? If I wish to explain you by a picture, and it is completely forbidden to use the space not belonging to the surface. Here I draw a surface which sits in Euclidean 3 space. This picture should have the interpretation of a surface in Euclidean 3 space, So if you find this, so you take a piece of paper and glue it back and make this Möbel strip, then it sits in 3 space. So I wish to express that you cannot orient, but it is forbidden to use vectors which point out. How do we do this? How would you do?
I think that normally we say that what's this called? Terminal bundle? Too complicated. Okay, sorry.
But you are right. But how do you draw that? That everybody sees it?
We have to do with being able to reach every point from it.
No, it's connected. It's connected. If I have 2 points, I can go from one to the other. In many ways.
Yes, but what I'm saying, if I have these, I can go from the top to the bottom.
No, there's no top. What means top? The word top refers to the way you put the surface in 3 space. Yeah? If I take a coin and throw it, like, it's the only thing I know from football, and it falls down, there are 2 possibilities, and I forgot the names, like this or like this. But this refers to 3 space. This is not a notion in dimension 2. This refers to 3 space. I wish to have something. So this is out of the blackboard, and you don't see it. It's behind the blackboard. That are things which belong to 3 space. These are notions, words which are clever, which are clear for somebody who knows 3 space.
Yes, but still, I can make a difference. We are talking about normal vector.
No, normal vector is a vector which points out on the surface.
Yeah.
It's not sitting in the surface.
Right, but what I'm saying, if I stay within the surface, in counting vectors, at some point here, I reach the boundary and I can get to the other side.
No.
There are no
This is drawn, this boundary, but there's no boundary. It is not allowed to go there and then come back there. It's not allowed. It is drawn with boundary because it's too much time to draw like this.
Maybe you may describe like rectangle to glue 2 sides in the different.
Yeah, but it's also, if you take a piece of paper and you do this, then you do something in space. This is forbidden. You must give me a notion which belongs where it is only allowed to walk along the surface. And I wish to know surface is oriented or not oriented. I will draw it for you. What we do is, at some point, I take 2 vectors belonging to the surface. The first vector and the second vector. They belong to the surface. Of course, you don't see the difference here. But I say in words, they are tangent to the surface. And now we start walking. And I drag those vectors with me. So here I have first vector, second vector. And do this all alone. So when I come back, first vector sits here, and second vector sits here.
First vector to the left. Yeah.
No, not this.
Use 2 colors.
No, I use arrows. This is color 1, this is color 2. I see. This was at the beginning, and this is at the end. And so now what we see is there's no way. So when we in the plane, we have 2 vectors. And we have another place we have 2 vectors. Then it is not possible to walk from here to here, keeping the vectors independent, and going from this picture to this picture. And the fancy way of saying this, we take tangent plane, and the first system of vectors was a basis, the second system of vectors was a basis, and the change of basis goes by a linear map. And this linear map has a determinant which is negative. And then we go to the determinant boundary story we heard before. So we work with this kind of surfaces. And this is on the purpose of simplification. Riemann surface concerns also more complicated surfaces, but we want to have this kind of surface. I must say, if you drop the convention, the simplification oriental, then there will be no G. But this we see later. So, connected compact is for purpose of simplification. Oriented is for purpose of having our second step in next lecture. So, now, can we make surfaces which are connected, compact, oriented? So question. And some mathematicians sometimes say, can you make something? Other mathematicians say, does there exist something? And to make very clear, I say something which everybody understands, can you buy such a surface? And if you can buy it, then I think it exists. So the purpose is now we wish to go outside of this building and buy such a surface. And what is allowed is to buy pieces in the shop, such that at home we can make the surface. So we buy this kind of things. Everybody knows that if you wish to make waterproof for your bathroom, better buy such pieces. It's called a T-piece. Then probably you need also tubes. And then perhaps if you do this, the water comes out at too many places in your bathroom, so you need caps. And I give you a supply of this kind of things. Then you can make a surface.
Is that an exhaustive list?
Yeah, I think for the city
because when I go to the superstore, I mean to the store, okay, for the irrigation system of my house, I also have other pieces, like for instance,
but we go to a very simple shop. Not your shop. We only have this kind of. You know, you could also have these which look like this. We'll come with 4 outlets. But this is too complicated. And if you wish to have such a thing, and you have only this kind of shop in your village, you wish to have a thing with 4 outlets, it's very easy. You buy two D pieces, and you put them together here. Then you have a thing with 4 outlets. So this is enough. Then you can even make such things where you have 4. And 5 and 10 and everything you want. So let's try to make a surface. I draw for you here a surface. And it's important to understand this drawing. So everyone understands this drawing? You should say that this, you have this. So such a surface. In some bakeries you can buy such a thing. Mostly you eat, the inside is why you buy it, you don't eat it, but the boundary of that thing, there are more complicated shapes in the bakeries. This is the surface.
Is that like the two donuts glued together?
You don't know what is donut. But probably yes. Probably yes. I wish to show you that this is, I can make it with this. So what I do is, I cut here, and here. Then the top is such a piece. Because it is something with three openings. And the bottom is also such a piece. So this equals to 2 times t. This is a t piece. But there are many ways of doing this. So I try to draw the same surface. I get cut here. And then I cut here. So this opens. What is on the left is a T piece. This is just the same as when I take a T piece and glue both ends to each other. But if you do not want to do this, what you can do is you can also buy a tube. Then you see here the tube. Here you see a T piece. So you have a tube and a T piece. And on here you can say one tube and then another tube. So I have a tube and a T piece. So the given surface can be decomposed in many different ways. So what we want is, we want to have a way of recognizing if two surfaces are the same. Of course, they do not look the same, but the same means you can deform one and the other without breaking it. So there are more fancy words in mathematics to say exactly. And so there are two notions which are important for further thing in our it's the notion of genus. The traditional letter for this is G. It was invented by Riemann. His traditional letter was P. If you look in the Riemann papers, you do not see a G, you see a P. And then there's another thing, is other characteristic. And typical letter is this. And then again, historically, if you look in Euler and you look at his definition, you find not the definition we use, you find the definition just the opposite. So, I wish to explain this issue.
But did Euler go that way, or that is the interpretation of Euler nowadays? Because if I remember properly, the Euler characteristics had to do something with the sum and difference of number of faces and number of edges, and, or is that another theorem thing?
I only say that the result differs by sign, and it did not say that the introduction differs at many places. The way Euler did it, Euler was not doing strictly speaking topology. Euler used measurements to introduce Euler characteristics. size of angles. So he uses measurement. And then his statement was, the result is independent of the measurement. But his definition used measurement. Then it took many years, perhaps 100 years, to make a definition which does not use measurement. No notion of angle. And so the way of explaining our characteristics changes over the last 200 years, 200 something years, drastically. And what I tell here is something which is perhaps 100 years old.
Old?
100 years old, only 100 years old. If we add all ages, we go above 100.
Could I
So it's
say,
not so old.
yeah, when we look at the Euler characteristic, suppose I don't know what the Euler characteristic is, and I go to book on analysis like,
Should never do this.
yeah, but you weren't available there, so.
No. No. What you should do is, you should open the book, look the content, think yourself what should be in the book, and then eventually at the very end you check if you are right or wrong.
By then, I have run out of money. I sold my house.
Because if you read something about mathematics, there's one possibility is you don't understand. Then you forget immediately. The other possibility is it's so easy that you immediately understand. Then you forget next day. So the result is the same after 2 days. But if you think yourself about something, it stays at least 3 days. So this other characteristic, we ask something which I do not ask here, we ask that it is additive. I wish that our characteristic of A union B, and union means cube union. That is along the boundary. So when I put two cubes together, I glue them here. That is one boundary circle, and then we mention the other boundary circle. And the same when I glue a cube to this. So this is, perhaps I should say, when I glue along the boundary circles. This simply means you put together along the boundary circles. And we add something which we like to do in algebra. We wish that this is the sum of both. This is, we wish that our characteristic has additive meaning. Of course, additive meaning depending on some conventions. The conventions here was we only glue along boundaries. We do not glue in other ways. And then we ask another thing. Chi is topological. So we look for a notion. We look for this number which is attached to a surface. We look for a notion which has those two properties. I must perhaps say what it means chi is topological. Chi is topological means if you have two surfaces which are topologically the same, I will say this better, then the chi should be the same. Topologically the same means there is a map from the first surface to the second surface, which is bijective and continuous in both directions. Then you say two surfaces are the same. Examples of two surfaces which are the same is if I take a D piece and I had a cap. This is the same as a cube. It's clear, right? The cube has the water goes in, out. Here also water goes in, out. But if this is cube is double, right? here kind of exile. But topological is the same. This I can deform into a cube. I wish if two things or topologically the same kind. So in formula means chi of A equal chi of B if A topologically the same, top the same as B. So from this I can already say what is chi. Because we use those axioms. So what is chi of a cube? So question, chi of a cube. So what is this? So what we know is chi if I add the cube and means union along a circle, putting two cubes together. Then I find again a kind of cube. Perhaps I forgot to say here something about this chi. Chi is so good that we can compute with it. So everyday learning means chi is a number. Chi of the surface is a number. So from this, if this number has the property, let's call small t this number, we have t plus t is t, and if you did not go to university, you conclude t is 0. If you go to university, perhaps you don't. If you did not go, clearly you conclude this. So chi of a cube is 0. Then, if I take a chi of the d piece plus chi of a cube, this is chi of a cube, no, chi of a cap. This is chi of a cube. But the picture I did here, the d piece plus the cap makes a cube, topological. So from this we see t piece, the number t piece plus cap equal to 0. So that means if we wish to say what is chi, we only have to decide freely what is chi of, say, t piece. So if chi of t piece is fixed, then chi of the surface follows. Because the surface you can break it in pieces. The tubes, they are for free. The t pieces, the gaps, they compensate each other. So you look, do you have more gaps than t pieces? Then you have gaps. Or do you have more t pieces than gaps? This is the term chi. So let's make a convention. Chi of a gap is 1. So Euler made a convention chi of a gap is -1. Nowadays, chi of a gap is 1. Then chi of a d piece is -1. And chi of the surface is, you break it in pieces, you count the d pieces, the gaps, everything, you follow those rules and you have chi of the surface. So let's do chi of 2 here. This is the same as chi of a cube with kept off twice. Then I have two spheres. Around the North Pole, I remove something, South Pole, I remove something, then I get 2. And here there are no key pieces, only 2 gaps. Gaps was 1, is 2. And chi of this term is how much? Minus. So, the very amazing thing is, if we stay in the world of this kind of surfaces, then there happens a very big theory. So, if A and B belong to this world, so a surface which have those properties, and if chi of A is chi of B, then A is topologically speaking the same as B. Such a statement is called classification. What we did, we have some things which are complicated, this kind of surfaces. We make, for them, we make something which looks more simple to us, like a number, like an integer. And then we have if the added integers are the same, then if the integers which you get are the same, then the surfaces or technical word is homomorphic, they are topologically the same. I think in modern world, unfortunately, one does this not only with surfaces but even with persons. In some countries you have a text number, in other countries you have a security number, and the axiom is there are no 2 different persons with the same text number, same security number. So that number is as good as knowing the person. Here, this is a typical example of the classification theorem. So, this is the way of getting a number attached to the surface. You force axioms, first you wish to get a number, chi of the same should be a number, then you wish to have some algebraic rules, additivity, and then it should be, you say, if you have 2 objects which are topologically the same, you should have the same number. Those 3 simple rules produce a number for surfaces of this type. And this number is so strong that if 2 surfaces get the same number, the same characteristic, then they are homomorphic. That's the reason.
I have a question. I can say that 2 substrates are the same if I can transfer one to another.
Then you can also be, as if I say yes, then you can also be what means transform. So first I say yes, and then I say something more. So, in topological spaces, I wish to say they are topologically the same. The technical word for topological the same, if you open a book like I was proposed a few minutes ago, the technical word is homeomorphic. Homeomorphic. That means The meaning of topological same is, so definition of this, I write the definition here, there exists the map from x to y. This map has properties. First property, f is continuous. Second property, f is bijective. And third property, f inverse, is also continuous. So, just as test, consider this X as a topological space. This topological space, if you wish to go to the shop, you buy 4 such things, and then you glue them together like this. And this is cheaper. And you only buy 3 such things and glue them together. So question, all those 2 spaces, which one looks like letter X, the other looks like letter Y, all those 2 spaces homomorphic. Or they topologically the same. What is it? All the topologically the same. So here I say definition X is topologically the same as Y. X and Y are spaces. Then comes definition. There exists a map from space X to space Y, which has property, bijective and continuous in both directions. Here, the question is, consider this picture as a space. Space, if you draw it, looks like letter X. Then consider the letter Y as a space. Question, all those spaces homomorphic. Or all those spaces topologically the same. Here I see this on infinitesimal level.
Because we can just refer to the 4 points cube, you know, that you showed before, and the 3 points, the 3 is cube.
They are the same or not the same? Not the same. What is the proof?
If you remove the process.
Okay. If you remove this point, you get 4 pieces. You get, technically speaking, 4 connected components. And if you remove this point, you get only 3 connected components. A connected component is a maximal subset, such that in this subset, 2 given points can be joined by a curve. So when I remove this point, I get back the 4 pieces. And then if I take 2 points here, now I cannot connect. Here I can connect. Here I cannot connect. So now I take biggest possible subsets, such that in that subsets, 2 points can be connected. So this is the biggest possible subset in connected component. This can be 4 times. So when I remove this point, I get 4 connected components. When I remove this point, I get 3 connected components. To be a connected component is a topological notion, so I get different answers. So if you are chemist and you wish to distinguish, say, benzene from water, then you do an experiment. You can perhaps smell. I imagine you do not like to smell, but you can do it much easier if you take a match. One burns, the other does not burn. And then you say, they are different. Here we do the same experiment. Remove as you propose point. I get 4 pieces. Here I remove a point. I get 3 pieces. If technically speaking, you must show that if you here remove a point, you never get 4 pieces. When I remove this point, I get 1 piece. When I remove this point, I get 2 pieces. And when I remove this point, I get 3 pieces. So each time you remove a point, you never get 4 pieces. So therefore, this and this are different.
But if you consider point in infinity,
There is no infinity here. This are pieces bought in a shop. And there are no infinite shops in this city. So, let's go to definition of genes in the way Riemann. So this is a classification of surfaces which are restricted to be of this type. There's another way of doing this, is the notion of genes. The notion of other characteristic is very good in many applications. The notion of genes is also very good in many applications, but there are applications where one of them is better than the other. So therefore we need both. So, genes. So, we draw again the surface, the same as before. First, the bad definition of genes. Here, you can look through at 2 different places. If you go to the bakery, buy this thing, you put it like this, you can use it as glasses. You go to the bakery, you buy this, and you have your glasses. So this is genes too. But again, this definition uses the way how you put it in 3 space. And it could be that the big thing was folded such that this area covers this. There is no way of looking through. So this is a wrong definition. But it's very practical. You immediately see this is a gene. I give a better definition. So G is the maximum number of simple closed curves on the surface as it is on S that are pairwise disjoint here I should say that exists on S that are pairwise disjoint and do not disconnect the surface. The maximum number of simple closed curves that you can draw on the surface that are pairwise disjoint.
A number, we mean complex number, real number, integer number, because there are many numbers. How do you use number? What means number?
I said maximum number. So that excludes the complex numbers. No maximum number. No, so this this is related to very primitive complex. So these are natural numbers.
Natural? No negative?
No negative. If you can draw no such curve, then your number is 0. So it is natural number not older than 3,000 years.
All the characteristic is integral.
Order it could be negative, it's an integer. Here, it's
But this was missing in your definition.
no.
Never defined.
No. In my definition, I said you take a number with which you can count, you assume. So you're free to take any set of numbers. What I asked you to take only sets of numbers on which you can count, with which you can count.
The meaning complex number is not number. Complex
It's also a load. If you say that kind of what they say, if is fixed, you can fix by the golden number. Imagine you like the golden number. Then here I say only if you fix chi of a piece, then chi of every surface is fixed. But which number you take does not count. Then we go on. I say our convention is we say chi of a cap is 1. We know already that chi of cap plus b. And then we continue. When you're completely free to fix as you like.
So the only characteristic is integer so on.
If you are fixing that way, you could also say 10 stays integer. But if you say chi is a half, then by magic, chi of the surface is still integer. You will see this later. But if you do chi is 1/3, but you are completely free in the first fixing. So, I forgot where we are. We are on this level. Here. The genus is the maximum number of simple closed curves that exist on the surface that are pairwise disjoint and do not disconnect the surface. So let's do this. We take a surface, a sphere. So what is a simple closed curve? A simple closed curve is a curve parameterized by numbers. The parametrization is injective, but it's closed, so the beginning point and the end point are together. And simple means the curve during its travel never crosses each other. So such a curve is not a simple curve, because if you start traveling, you come twice at the same point. This curve is simple, but not closed, because at the beginning and at the end, we have different points. Closed curves are like this. So now I draw on the sphere a simple closed curve. And you also behind, but I cannot draw. Each time when I do this, I get two pieces. This was obvious for Riemann, but it took, I think, 50 years to prove it of the Riemann. But here we see how the definition works. When I remove one simple closed curve, I have already two connected components. This point and this point I cannot connect. If I try to connect, I have to go through that removed curve. So the number of simple closed curves that you can remove, and the relating stays correct, so that's not discorrect. This number of simple closed curves is 0. So genus is 0. Let's take next surface. Torus. If you remove this curve, which is a simple closed curve, this is one curve, and what you get is a tube, and the tube is connected. So what we have is genus is bigger than equal 1, because we can remove one such curve. So if we remove one curve, you get a tube. If I remove only the tube, you get the curve. It disconnects. These are all statements which look obvious, but to prove is not so easy. Because here, when I remove this curve, I get the tube. Perhaps when I remove some other complicated curve, which I do not see, I get something different as a tube. There exists also a curve which disconnect. When I remove this curve, I get two pieces. I get this gap and something else. So, when I believe that when I remove a curve and this does not disconnect, that I get a tube in this situation. And from a tube, I cannot remove the curve and keep it connected. And there are essentially two kinds of curves, which go around, then I have two tubes. Or which do this, then I have a gap and a key piece. So, genus is 1. Genus of this thing, I can remove this curve, I can remove this curve, stays connected. So genus is bigger than 2. But when I remove those curves, I get something which is like this. Now I say that I remove the curve from this and this connects.
We can take the tube and cut the line.
The line is not a simple closed curve.
The line is
It's not allowed because it's not a simple closed curve.
close.
Now, how can we maximum? How can we be sure that in a more complicated case, okay, how does one know whether we have a maximum or not?
Even in this case,
That's a simple one.
no. No, this is Norbert A'Campo. This is most people on this planet cannot prove this.
Small g. I'm saying, assume we have a curve with a big G.
Yeah.
A substance with a big G.
Yeah.
How can we know?
My answer is as follows. Assume you are very rich. Assume you are very rich.
That's very good. Okay, go ahead.
Assume this. And assume also somebody forces you to tell how much money you have. Then you must look at maximum. Yeah? And if this maximum is one more than what you think, you are not rich. If you are poor,
Okay.
you have $1 more, you are already rich. So I would say the difficulty is not in the big surfaces, this big genes. The difficulty is hidden in the small surfaces.
Okay, wait, okay.
Because what we can do is
You are telling me the question, it doesn't matter.
what I'm telling you.
Okay. Surfaces that one can describe, so to speak, okay? What are typical G's? G0, G1, G2, that's 5. If I ask you, give me something that has G equal 5.
Yeah, I give you answer. No? I give you the first answer was 1% honest. Next answer is 99% honest. So to go back to this other characteristic. So what we do is we decompose our surface in dp's, tubes, and so on. And now we do the following. Each time we see working with, we have many things like this and tubes. So what we do is each time we see a tube, the end of the tube is attached to something else. It could be that it is attached to another tube. Then what you do is you glue them together and then you make sure you have one tube less. It could also be that you are attached to the deep-piece. Then you attach this tube to the deep-piece. It stays the deep-piece. So what you do is you kill all two